For this lesson, I want to look at the graphs of general quadratic equations. So any quadratic equation has the form y is equal to ax squared plus bx plus c. We've looked at a few of these before, like y is equal to x squared, it has this shape to it. But if you compare that to something like y equals 2x squared minus 5x plus 1, it's the same general idea, it just has a different location. It looks like the x squared graph, but maybe it's moved a little bit to the right and then down a little bit. One thing to help us understand the graphs is by looking at a very particular spot, in this case something called the vertex. That is the lowest point on the graph x squared, so it has coordinates 0, 0. If you know where the vertex is on a quadratic, you have an idea of what the general shape of the graph is and where it's located. So for example, the vertex on the second quadratic equation is here, so I'll just highlight it. But, what are the coordinates? What's the x and y value that represent this point? So to understand the graph of a quadratic, what we're going to do is take this thing and write it in a way that tells us how the graph moved. So starting in example 1, I graphed the function, in this case, y equals x squared minus 8x plus 19, and I got this shape here. But it turns out, if you were to graph y equals x minus 4 squared plus 3, you get the same exact graph, like these two overlap each other perfectly. That just means that this one graph can be written in two different ways. If you check out the way that this one is written, it's easy to understand in terms of transformations how the graph of x squared moved. By that I mean, we have x minus 4 squared. This is changing an x value. I know that means, okay, we're going to go right 4 places. This plus 3 outside the function means we're going to go up 3 places. In terms of the vertex of x squared, if you start at 0, 0, and you go right 4 and up 3, it tells you that that's the location of the vertex. So that was the points 4, 3. So if you have a quadratic and it looks like this, it's much easier to understand what the graph looks like, as opposed to this. It's just written in a way that's not easy to graph. So for this example, I want to show that these two equations are in fact the same. The way I'm going to do that is by taking this, squaring it out, combine some like terms, and hopefully end up with this equation. So let's try that. We'll start with y is equal to x minus 4 squared plus 3. To multiply this out, I have to square x minus 4. So I'm going to write this as x minus 4 times x minus 4 plus 3. To multiply x minus 4 times x minus 4, I have to use the distributive property, or if you like, FOIL, where x gets multiplied to x, it then gets multiplied to negative 4, and then we do the same thing with negative 4. That gets multiplied to this x, and then to the negative 4 at the end, and we'll end up with 4 terms. So let's multiply all that together. Okay, x times x gives me x squared. We have then x times negative 4, which is minus 4x. Moving on to this negative 4, that gets multiplied to x, so we get a second negative 4x. And then we have a negative times a negative, so it's going to be a positive, and 4 times 4 is positive 16. And then this plus 3 tags along. And we're practically done. We just have to combine the like terms. We have y is equal to x squared. A minus 4x is a total of minus 8x. And then 16 plus 3 is in fact 19. So that's why these two equations are the same. You can just take this thing, multiply it out, combine like terms, and it would take you to this. What I want to do is come up with a process that reverses this for us, where if we start with this equation, how can we do this process backwards to end up with this type of an equation? And it's this process that we call completing the square, going backwards, taking us from this second equation back to this first one. So I'll just jot this off to the side, that completing the square is going from one form to the other, specifically this expanded one to this more condensed one. One useful observation will be the following. If you look at this -8 that appears next to the x, half of that value is always going to appear within the parentheses here. And the second thing to point out is, so let me actually write that down first. If you take that -8 and you divide it by 2, it gives you -4. This number shows up within this process. And that happened because when we multiplied it out, it doubled to combine to this -8. The second thing is, if we square this -4, so I'll write that here, it turns into a positive 16. And that is the number that goes right here. Understanding the connection between these three numbers will be important for completing the square. It works like this. We would start with this expression. I'd look at this -8. Half of that number appears here. It's then the square of that number that shows up here. So for example 2, what I'd like to do is take this quadratic and complete the square on it. What that's going to do is tell me what the graph looks like just by using transformations. So I'm going to go through a general procedure for this. To complete the square on y equals x squared plus 4x minus 7, I'm going to get the x terms by themselves by adding, in this case, 7 to both sides. So that is y plus 7 is equal to x squared plus 4x. And if there were a number that wasn't 1 in front of x squared, I would divide both sides by that number. In this case, it was 1, so I didn't have to do that. The trick to this problem is you want to add a number to both sides of the equation. So I'll put a spot for that. We have y plus 7 plus something is equal to x squared plus 4x plus something else. I want to add the same number to both sides of this equation, but I want to choose a number that when I put it here makes this piece a perfect square. To get that number, you can look at the value that's in front of the x. I'll jot it down off to the side. It's 4. And we're going to take half of that number, which gives us 2. We then take that number 2, square it, and it gives us 4. It is this number that I add into both sides of my equation. So I put a 4 here and a 4 here. So I took my equation, solved for the x's, and I added 4 to both sides. On the left, I get y plus, I can now combine the 7 and the 4. That's 11. And this is equal to, I'll just copy it down again, but we have x squared plus 4x plus 4. It should be that these three terms you can write as something squared, x, in fact, plus something squared. And once you know what that number is, we are very close to done with this process. And it turns out that number is this 2. To rewrite this whole thing again, we have y plus 11 is equal to, and I have x plus 2 squared. It might be worthwhile checking out why this in fact worked. So I'm going to do that off to the side, where I want to take this x plus 2, square it, just to verify that it's giving us x squared plus 4x plus 4. So let's see. I have x plus 2 squared. That's x plus 2 times x plus 2. If I FOIL this out, I get x squared. That comes from x times x. I get 2x, which comes from x times 2. I get a second 2x, which will come from this 2 times x. And lastly, I get a 4, which comes from 2 times 2. I combine all the like terms, and I do in fact get x squared plus 4x plus 4. That's why this process works. clearly if you take half of this number, it would have to take you back to this 2. And when you square this number 2, it takes you back to the 4. All that being said, I have y plus 11 is equal to x plus 2 squared. To solve for y, you can subtract 11 from both sides. And this is the final answer. This is completing the square on the function. From this completed square, you can determine where the vertex is. The x plus 2 means you go left 2. The minus 11 means you go down 11 on the original graph, meaning that the vertex is -2 because you went left 2, and -11 for y because you go down 11.